Hi everyone. It's past 3:15. So I just want to thank you guys all for a wonderful workshop so far. And I would just like to introduce our next speaker, Professor Michel Devoret. He is currently a professor, a visiting professor at the University of Santa Barbara.
No, actually, I am a professor.
Oh, it's doing it now.
I'm not just visiting.
Okay, he's a permanent professor at UCSB. He's also working with Google Quantum AI. And he has a number of very distinguished accomplishments in the field of superconducting qubits, too many for me to probably list. Please give it up for Professor Devoret.
Thank you. Thank you very much, Lodi, and thank you to the organizers of this very nice workshop. So yes, so I would like to continue what I was discussing in the previous talk, which was a beginner's introduction to circuits. Here I want to focus on the problem of constructing Hamiltonian from a circuit diagram. And maybe one of the most important words in this title is A here, because there's not such a thing as the Hamiltonian of a circuit. From a circuit, you can construct a whole series of Hamiltonian, which are all equivalent in terms of the equation of motion and the physics. But depending on how you start and what method you employ, you could get different Hamiltonians, and they might allow you to see certain things that some other Hamiltonian would not give you. I would like to acknowledge my former colleagues here for the discussions that led to these slides here. There are many concepts that have emerged through the several years of practice in this field of quantum circuits. And it's very interesting for me to see that a lot of the publications in the 80s on this subject contained actually quite wrong results. So I think that things have stabilized right now, and what you read are more or less true, but it's still a subject in evolution. Okay, so I hope to cover this, but maybe I won't get to the end. It doesn't matter. What counts is that I answer your question. So I want to make this talk really interactive. So if there's something that bothers you, something that you always wanted to know but were afraid to ask, this is the moment. Please interrupt this talk. Okay, let's start from a circuit diagram. I have chosen here two transmons which are tunable, and they are coupled by this coupler, and then they are read out by these resonators here. This is just an example, but just the question is, how do we construct an Hamiltonian for this circuit diagram? I should not maybe forget the ground here. This is going to be important later on. Okay, so here is how the story starts. So you have a circuit. So a circuit in electrical engineering, it's an arbitrary network of electrical elements. So each electrical element is a box here, this a rectangle box, and connected, and two or more elements can arrive at a node here, and each element is on what is called the branch of the circuit. And then there's a third element, a third concept, which is the loop. So the loop is a path consisting of branches that return to its origin. So something very important to learn from the very beginning is what we call the voltage of a branch. A branch actually is defined by its two extreme nodes here. And as you can see, the arrow for which the voltage is with which the voltage is counted and the arrow for the counting of the current are opposite. This is a trick, a very useful trick that removes all the negative signs in electrical formulas. So you have minus signs in Maxwell's equations, but in circuit theory, with this choice of convention, then there's no minus signs. So what does it mean? It means that this arrow means that if the potential would increase from this point to this point, then you would count it positively. And if your current would go in this direction, you would count it also positively. So this is what the arrow means. Now, what do we call exactly the voltage and the current? Well, these are integral of local electric fields. So the voltage, what we call the voltage between two nodes, is the integral of the electric field along the branch. And the current through the element here, through a branch, is a double integral of the current density flowing through the branch here. So to each element, so an element can be inductive, and it can be a linear inductance, and that means that the voltage is related to the current by this relation. You can instead give the energy as a function of the current. What we call an inductance is the fact that the energy of the element depends only on the current and not on the voltage. And the capacitance is a dual element. There's the energy stored in the element depends only on the voltage. If you want, inductances and capacitances are bottles for electric and magnetic fields. So circuit applies to the situation where electric and magnetic field do not coexist in space. So, and they are in separate bottles if you want, and then each bottle can be represented as an element. There's a very important element, which is the Josephson inductance, which has a voltage related to the current by this relation, but this is only kinetic. It's unlike the magnetic inductance. It is the energy, the kinetic energy of the electrons inside the element that creates the fact that the energy is actually of inductive form. So these elements have different voltages and current, but the problem that we have to face is that all these variables are not independent. So you cannot say that your degrees of freedom are all these voltages and the currents for all the branch of the circuit. You overcount the number of variables if you would do that. So this is the main problem, actually, in writing the Hamiltonian of the circuit. You have to find the right set of degrees of freedom. And the constraints that you have is that around all the loops, the sum of the algebraic sum of all the voltages have to be equal to 0. And we have the other Kirchhoff's law, which says that the sum of the current flowing into branches that are all incident to a node also should sum up to 0. And something that you may not be aware of, but if we take the constitutive relations and we add Kirchhoff's laws, that's exactly equal to Maxwell's equation, of course, on a discrete network. So we are not, this is absolutely equivalent. Again, sorry, there's an error here. The branch voltages and the branch currents are not independent variables. So our mission is to find, to get to an independent set of variables. So this is what I'm going to do in the remaining of this talk, is to give you a method in, let's say, 98% of the cases, arrive at this construction. Okay, so we are going to do eventually a quantum treatment of circuit, and then this imposes to not deal with current and voltages, but by their time interval. So this is something that I will show you. We have to not work directly with current and voltages, but their time interval. So we define the generalized flux here. So any element that has a voltage across it will have a flux, even if it doesn't look like an inductance. For instance, a Josephson tunnel junction doesn't look like a coil, but you can define this generalized flux by integrating the voltage. So it depends on the history of the voltage, this flux. And the same thing with the charge that has traversed the element. It's the time interval of the current. We like to think of this flux as a position variable, and this charge as actually a momentum variable, for reasons that will become clear later. Indeed, if we take the commutator of the flux and the charge for a branch, it behaves exactly like the commutator of the position and the momentum of a particle. So you can think of essentially a branch like this as a sort of particle, but of course, it is linked to other particles by all the connections in the circuit. Once you have introduced this flux, you can compute the energy of a Josephson junction, and you see it's a cosine function of this generalized flux here. It's not a magnetic energy, it's an energy associated with the acceleration of electrons across the barrier. So we have to revise Kirchhoff's laws here because we take the integrals, the time interval, the sum of all the fluxes around the loop now is going to be a constant. It's not zero. With the integration, you find the constants here in this Kirchhoff's law. Why do we focus on fluxes and charges? Well, it's because that there are commutators of E and B, and therefore a commutator of E and V. But you look at this complication. So we could do quantum electrodynamics directly on the electric fields and magnetic field. But look at this full commutator. This is pretty much, what quantum field theory tells you. But look, you have delta functions. It's not never very nice to have delta functions, but it's the gradient of the delta function that enters in the commutator. So this is why, well, you could do all quantum circuit theory using this, but this is, I find this much more user-friendly. The fact that we have this commutator, which is equal to, this is way more friendly. The commutator is a constant, not a function itself. Okay. Now we have posed the problem. So we need to find pairs of conjugate variables to put in our Hamiltonian, and this is our mission. The Hamiltonian is a function of these pairs of conjugate variables, eventually of time. And the Hamiltonian is obtained by taking the sum of the energy of each branch. But the problem is that you have to express this energy not as a function of the flux and the charge of that branch, but that of you have to transform this expression and write it in terms of pairs of independent conjugate variables. So how do we find these pairs of conjugate variables that are independent. By the way, independent means means that inside the pair you have this commutator, but all the other relations of commutation are equal to 0. Okay, so so there are different methods, but I'm going to concentrate on what is called the method of nodes. So we are going to concentrate on the nodes of the circuit here, and there's going to be one node that is going to play a role, a special role, so it's marked in black here. There's a competing method where we, instead of focusing on the nodes of the network, we would concentrate on the loop, but this is possible, but this is in general less efficient. So we are going to concentrate on this first method. So I have chosen a generic circuit that topologically represents all possible cases. So it is this circuit has the virtue of not being too complicated, but it contains every possible case that you might encounter. What does it mean? Well, it has a sufficient number of inductances and capacitances so that you can look at the various loops here, and they are of all the possible types. So, for instance, here you have a loop where you have only inductances, but here you have a mixed loop where you have inductances and capacitances, and here you have a loop where you have only capacitances. So you have all types of loops that are represented here, and you have also all the possible nodes. For instance, at these nodes you have an incidence of inductances and capacitances, but here you see there are only inductances that meet here, and here there are only capacitances that meet. So you have a representation of all possible topologies, circuit topologies in this example. This is why I am treating it. Now you see there's in this circuit 3 active nodes, so which are marked in white here. What does it mean, an active node? It's a node in which you have capacitances that meet inductances. So these nodes here are not active because at this node you have only inductances here that meet, and here you have only capacitances. So what you do is you separate 2 networks. So you separate the network of inductances. So this is the red network. And then you separate out the capacitive network, which is in green here. And as you can see, the 2 subnetworks are linked at what is called the active node, and then I have taken all the active nodes and separated these active nodes into 2 subnodes, but in fact they are connected here. So the subnode red belongs to the inductive networks, and the active and the node in green here, it belongs to the capacitive network. Okay, so you can always do this in any circuit. So now the next step is to choose one of these active nodes and to declare it ground. So, so this is going to be a reference, and we have to be very careful because this is an RF circuit. This is not a DC circuit, and the notion of the voltage of these other nodes with respect to this node is really tricky. And I have to spend a few minutes dealing with this question. So we privilege this node, and by definition, the potential here is going to be 0. But look at how we're going to define the voltage at the other nodes. This is a crucial step. So we have, in addition to the ground node, we have to choose what is called the spanning tree. And to simplify here, I have chosen a spanning tree that goes through the capacitive network. I could have chosen a more complicated spanning tree that would go through both the capacitances and the inductances, but here um, it's a good practice. It's usually simpler to just use the capacitive network. So I'm going to go from the ground here to all the active nodes only once. This is the definition of a tree. So this branch is left out. So that gives me one possible tree. Then I have the second possible tree where this branch is left out. And then finally, I can leave this branch out. And these are, for this simple example, that's only the three spanning trees that I can construct that go only through the capacitances. But you can see that with a very large network, I would have a lot of possibilities. And it's very, very important, this choice. So you have to choose the ground and you have to choose the spanning tree. And this is exactly the same as choosing a gauge in electromagnetism. You know that if you want to integrate Maxwell's equation, you have to do this in a particular gauge. This is a sort of a reference system for electromagnetism. It's a sort of coordinate system. Well, in circuits, this choice of gauge corresponds to a choice of ground and a choice of spanning tree. So now we have a spanning tree, we can define what is called the node flux. So this is a bit bizarre because if you are used to the fact that a flux is through a loop, here it's a flux associated with a point. So it looks a bizarre notion. But remember, I have defined flux as an integral of the voltage. Yes? Yes, yes, it's always possible to find because the spanning tree has to link the active nodes, and the active nodes are by definition they have some foot in the capacitive network. We can talk in some complications that are not actually problematic. You have to forgive me. I am leaving out some marginal cases here, which demand a longer discussion. But I think by and large, as I said, what I am talking about will solve 98% of the cases. You can always find, essentially weird cases. Okay, so how do you define these node fluxes? So we're going to assign the flux to each node, but how do we do this? Remember, I can define for every branch a flux by integrating the voltage across that branch. So what I'm doing here is that I am integrating the voltage, actually the electric field along the tree up to that node here. So you see that in these three cases, the fluxes will not be the same because here phi1 is the integral of the electric field along this path, and here phi1 doesn't change, but phi2 is different because the phi2 defined here is the phi1 plus the contribution of this branch. But in this case, the phi2 is actually the phi of this node plus this one, this branch. So you see in these three cases, actually my position variables will be different. So you see, it's a bit like in mechanics, you could define the position in different coordinate frames. Okay, so actually I am detailing the algebra here. So you see phi 1 is actually phi A plus phi B. So these are authorized branch fluxes. And then phi 2 is phi A plus phi B plus phi C. But if I go here, I have different definitions. You see phi 2 is phi A plus phi D. And here, it is phi 1 which is changing. It's phi A minus phi B. Sorry, I made a mistake here. Sorry, this should be plus phi D here. Sorry, no, there's obviously a mistake in this algebra. It's phi A plus phi D minus phi C. I'm sorry. Anyway, okay, so I have defined the node fluxes. What are the conjugate charges? Well, the conjugate charges are the following. So the following charges will be the charges that flow from the inductive subnetwork to the capacitive subnetwork. So the charge which is conjugate to a node, so this is the charge of a node, that's the charge that flows from that node into the capacitances. And now you have identified the proper conjugate variables. So the big achievement here is that by doing this analysis, you have managed to find all the true dynamical variable of your system. Now you have to write the capacitive energy. So this is so you will have to write the capacitive energy of this of the capacitive subnetwork as a function of your two conjugate momenta, which are the charge of this node and the charge of this node. And so that necessitates what is called the capacitance matrix. So you can write the relationship between the capacitance, the charge of these nodes, and the voltage of these nodes. And this you can do at DC. You don't need actually to think about RF voltages because you're just finding some matrix here, which is in principle independent of frequency. And you can get this matrix here, and then the energy will be actually obtained by the inverse of this capacitance matrix. So after finding the capacitance matrix, which on the off-diagonal elements contain the opposite of the capacitance between the two nodes here, you can, by inverting this matrix, you can write the energy, and once you have the energy, you can use it in your Hamiltonian. And this will be the way you compute the capacitive part of the Hamiltonian. Now, the inductive circuit, well, in principle, you have to do the same. And we could talk also about the inverse inductance matrix, but here there's a shortcut that would also work, by the way, for capacitances, but I reserve this shortcut for this problem. So the problem here is this node, which is not an active node, but which can be actually suppressed to simplify the problem by what is called the star triangle transformation. So in circuit theory, when you have three elements with three different impedances, which meet at a point, which you can reconfigure this circuit, and find an equivalent circuit which has the three same external node, but in this way you suppress this internal node, and by applying this formula, you can go from one circuit to another, and that means that you see my circuit is actually equivalent to this new circuit. Of course, these inductances are not the inductances I started from. I have to use this kind of formula to compute them. But then writing the Hamiltonian in terms of this is now very easy. In fact, in this branch, I just have phi1 squared over 2L1. In this branch, I have just phi squared over this. And here, I just need to take the flux difference here. Of course, I should not forget this flux in the loop here. So there's an offset due to the fact that Kirchhoff's law around this loop involves the flux inside. So you can see that by applying these methods, I can arrive at the circuit at the Hamiltonian of essentially any circuit. Now, I would like to discuss how much time do I have left? Okay. Now I would like to really discuss something that, and this is where an interesting discussion between Zlatko and I will probably arise. There are certain circuits that are different from the others in the sense that they contain an isolated electrode, which we call an island. So what happens here is the fact that certain nodes in the circuit are surrounded by elements that have all insulators in them. So you might say that from what I have just said, so this is just a capacitance here, and this is a tunnel junction. These are two tunnel junctions, but I have said that the tunnel junctions were inductances like any other inductancy. But here I want to stress the fact that, well, this node here is not exactly like the others because around this node, you can actually form a closed surface that will pass only through insulators. And this is where Millikan's experiment comes in. You know that if you have a metallic electrode that is surrounded by insulators, it can have only a discrete amount of charge. The charge on that electrode should be a multiple of the electron charge. Now, if we think that all the electrons are paired here, it means that this electrode should have an integer number of Cooper pairs. And that, okay, so this poses an interesting problem, which took many decades to clarify. So I cannot resist to telling you about this topic. So, by the way, this is the equivalent circuit of this Cooper pair box, which, by the way, Cooper pair box and transmons are pretty much the same thing, as we are going to see. I'm just introducing this crossing box symbol, which just saves you some ink here when you give the circuit. Okay, so here is the Hamiltonian of the Cooper pair box. And here we have something that is a bit special because we have the charging energy. And now N, this big N is not a photon number. Hence my question to Zlatko this morning. N is the number of Cooper pair in the island. And its conjugate variable is the angle the phase angle, there's a phase difference of this island with the rest of the circuit. And okay, so you have the Josephson energy is related to the gap by this formula here. Okay, now this, if we look at a mechanical analog of this system, this is the mechanical analog. So the phase difference between the island and the main electrode is like an angle, and it would be like the angle between a compass needle and let's say, the field imposed by this magnet here. But what is nice in this analogy is that we can have a representation of what is the charge offset. So this parameter, which, by the way, the charge offset is something that is continuous. So n is an operator that can take only integer values. But this charge offset is just this voltage here, this gate voltage multiplied by this capacitance and divided by 2e. This variable is purely continuous, but this operator has only integer eigenvalues. And these integer eigenvalues are this angular momentum. It's the angular momentum operator of this needle in the frame of the laboratory, an inertial frame. This frame in which the magnet rotates is not inertial, and its angular velocity, which can be any continuous number, is equivalent to this charge offset. And there's a certain amount of caution here concerning the commutation relation. So you cannot really write that there's no such thing as an isolated theta operator here. This doesn't really work. I have written it here, but theta has only a meaning when it is associated with a trigonometric function like sine theta and cos theta. Why? Because theta is defined up to modulo 2 pi, but an operator is not allowed to have multi-valued eigenvalue. So this is the commutation relation, and they are not exactly identical to, they reduce to theta commutator with n equals I, but only you see when theta is very small. Okay, so this is the analogy, and so we have to pay, in certain cases, to this commutation relation anomalies. This type of problem doesn't happen in classical physics because it doesn't matter whether theta is an angle, which is a variable which is called compact, that takes its value on a circle, or whether you have the ordinary phase, which goes from minus infinity to plus infinity. Classically, whether your variable belongs to a line or circle doesn't matter, because you don't have the possibility of interference of the wave function around the circle. Basically, the physics is always local. But in quantum mechanics, the physics is non-local around this circle, and so you have to take a certain number of precautions here. And this is this question of compactness of the phase. So the usual phi, usually we like to call the phase, the round phase here, which is just a flux divided by this flux quantum, which takes a value on the real line. This is called a non-compact phase, whereas the Josephson junction phase variable, which is the phase difference between the two superconducting phases on each side of the tunnel barrier, that is an angle that takes its value on the circle. And this gives to the Hilbert space, there is a subtle difference in the Hilbert space of these two cases. So the Hilbert space of rotor is like a needle that rotates around one axis, or a pendulum. All these mechanical systems are rotors. It's a solid body that rotates around one fixed axis. Not to confuse with a solid body that can rotate around any axis. This rotor has a classical phase space, which is a cylinder, because the position variable lives on a line, on a circle, but of course the conjugate momentum lives can classically live on the line. But quantum mechanically, because of this special non-locality of operators, then in such circumstance of this cylindric phase space, this variable n here, as is discrete, takes only discrete values. Because if you want the interference effects around the circle. And these discrete values, which have integer eigen values, are both positive and negative. So this big N here takes values like +1, +2, +3, but also -1, -2, and so on. And this is not to be confused with what happens when you go to second quantization. So what Zlatko mentioned this morning was that if you have a simple harmonic oscillator, you have this phi variable and q variable. But instead of talking about this in phase and out of phase component of the oscillation, you can think in terms of photon number and its conjugate variable, the phase angle. And here, just to make sure that there's no confusion, I call little n the number of photons. And you see the photon number and the phase angle here of second quantization is just a polar representation of a dynamic that happens in the plane. So the phase space here is a plane, it's not a cylinder. So topologically, it's not the same thing. And so this manifests itself in the fact that n is also an integer. This little n is also an integer, but it goes only from 0 to infinity. There's no negative values for the photon numbers, whereas the number of Cooper pairs that have caused the tunnel junction can be both positive and negative. So a little bit of caution is here. And there are ways, so what I want to stress is that when you treat a Josephson junction with an island, you have actually two choices. You can choose this choice of representation of this choice, but you have to be consistent throughout your calculation. So mistakes happen when you start with this representation, and then at some point you switch to here, or vice versa. So this is not very good. So Zlatko has a method to treat the Cooper pair box using this representation, and because he goes all the way to the end, he doesn't make any mistake. But if you start with the Cooper pair box in this representation, and then you don't really go to the end of the consequences, then some chaos will happen. Okay, so let me explain what is happening in the Cooper pair box, in which you change the ratio of Vj over Ec. This gives me, by the way, a way to explain where the Transmon name comes from and rectify a mistake that you find on Wikipedia. So you see, as a function of Vj over Ec, the spectrum so you can actually compute exactly the spectrum of the Cooper pair box. And the Transmon regime is pretty much here. So this is the the line of separation basically between Cooper pair box regime where EJ over EC is small and the regime where it is large. As you can see, if we go to these points, we have a qubit here, but we have two levels here, and the next level is way far above. So this means that we have what is called the positive anharmonicity. So the energy difference between the state 1 and the state 2 is much larger than between the state 0 and the state 1. But when you look at this spectrum, you see T-volts, and by the time you reach here, actually you get to what is called negative anharmonicity. So you have the difference in energy between 1 and 2 is smaller than between 0 and 1. And this inversion means that you're crossing a boundary. And crossing a boundary in Latin is associated to the prefix trans. So trans means that you have gone from this Cooper pair box regime to this regime. And it's not that there's a transmission line in the transmon. Actually, there's not anymore any transmission line in the transmon. So this is, in my view, this was the reason why the transmon was called transmon. So you get, what is marvelous here is that you get essentially no charge sensitivity here in the transmon. And Jens Koch, who's here, has computed actually, has shown that, you see, the anharmonicity goes to algebraically decays with this ratio EJ over EC. But fortunately, the peak-to-peak charge modulation decreases exponentially. So you really win when you attain this transmon regime. So in the regime where the anharmonicity becomes negative, even though you're losing in anharmonicity, you're not losing as much as you gain in essentially becoming insensitive to the charge offset. So that's the merit of the transmon. It's a Cooper pair box in which you can forget about charge offset. Okay, well, I think that I should stop here. I would, there's a few slides, but I don't think that's important. I will leave, I will end on this slide. Thank you. Yes, so there's first Eli.
Start dealing with things like non-reciprocal elements, facelets, like some of these techniques, there isn't fine. Can you comment on some of the more specialized techniques?
Well, so facelift elements, yes. So facelift elements are they. But the facelift elements are sort of. So this is the case where you have an Hamiltonian like this, but instead of having some inductive variable like theta, which is a sort of flux, you have a charge here in the cosine. And here, instead of a charge here, you have a flux. So this is the dual. So basically, you can think of a facelift element in series with a capacitance as a sort of dual of the Cooper pair box, where you have an ordinary Josephson element and just a charging capacitance. In fact, I have some. One example of this facelift element is the fluxonium. So So here is a mechanical equivalent of the fluxonium. So if we have only a pendulum, we have a Cooper pair box. So the Cooper pair box is just a pendulum. But this, in addition to just a nylon here, you can instead have a loop. So instead of taking the junction of the Cooper pair box and shunting it by a capacitance to make the pendulum more heavy, instead you can put an inductance across the tunnel junction, which means that as you turn this pendulum, you accumulate, you pull on these springs here. And so you have this system, by the way, is able to count the number of turns because you accumulate energy in those springs. So the interference effect doesn't occur because now all the turns are inequivalent. And it turns out that in this case, this tunnel junction behaves as a phase-slip element. You can tunnel from one minimum of the phase to another. And of course, you could, so you can think of every Cooper pair box as having an inductance, a very large inductance across it. And that means that you're leaving the representation where you say that this flux here is a phase variable that lives on a circle. And then by imagining that you have always this inductance, even a very, very large one, across your junction, then you can go from this representation of the phase as a variable on a circle, as a variable on a line. And provided you are consistent with this method all the way to the end, you can think in the Cooper pair box in a completely different way. So in this kind of different way, the charge offset is no longer a parameter, but becomes actually a dynamical variable. And so, and this is okay if you know what you're doing. If mid course you change your convention because you have not fully understood exactly what your starting point was, then bad things can happen. Yes. Sorry, there was this question here first. Oh, so loops are not important if they are. So you see the reason why I was able to do this. It's because you see this. I was just I wanted to just avoid this loop, but this loop is it's not an active loop because it doesn't connect. If you want, there's no capacitance in this loop. So this loop is completely static. So just for convenience, I have used the star triangle transformation to eliminate this loop. Basically, the loops that are inactive, you can eliminate either by this matrix inversion or by successive application of the star triangle configuration. So let's go back to, let me explain what I am saying here a little bit. So you see, so the true loops are the loops that contain both type of elements. Those are active loops. You cannot reduce those loops. But loops that are only inductances or capacitances can be eliminated by this sort of star triangle transformation or by some kind of matrix inversion.
One last question from online. Is it possible for the capacitance to be convertible? It looks like you would without the capacitance.
Yes. Well, you can always invert capacitance matrices if you add always some little parasitic capacitances. There's always some residual capacitance between any node and the ground. So I don't think that's really a problem in general. There was a question from Jens. Yes, yes, absolutely. Yes, it's a pre-strain in the springs. You see, you could just change the length of the strings so that at equilibrium the rest position is not vertical. So this is an offset flux. It's yes. Go. If you can find an electrical analogy to your electrical circuit, then usually any problem in quantization is lifted because we have a much better intuition of canonical quantization in mechanical system. For one thing, in mechanical system, the Lagrangian never poses a problem because you know what is the kinetic and what is the charging energy, what is the kinetic and what is the potential energy. Electrically, you have to go back to the magnetic and electric field. So the magnetic energy is the potential energy in quantum electrodynamics, and the electric field is the kinetic energy. But when you deal with the circuit, it's not always easy to go back to the basic underlying field. Yes.
Clarify, we were saying go from the rotor representation to the planar representation. That doesn't mean it's not that you're taking it to the limit where the phase is very small.
Oh yes. By the way, this you can see that you see what happens. By the way, if your phase excursions are very small compared to 2 pi, it means that a cylinder, if you take a very small portion of it, it will be always a plane. So you see that if your phase and charge excursions are not very big, you can go back to this scheme, and that's basically one method. This is why we can use annihilation and creation operators for the transmon. But that that means that you should never go around. You're completely neglecting the processes by which the phase goes around this cylinder.
What kind of processes are these? Like, a typical system counter. Where does the fact that it goes around the circle?
Oh, so the manifestation of the phase going around is offset charges. There's no way you're going to find offset charges in. I'm looking at Zlatko because, in fact, so if you there's never going to be offset charges if you go in second quantization, defining A and A dagger as a combination of flux and charge. But you will eventually recover this notion because what you find is that in the cosine potential, you will have bands. And now the quantum number, which tells you where you are in that band, plays the role of offset charge. But you see, in doing this, you have done something, a huge change. So something that was a parameter before has become an operator in a bigger, larger space. So, and there is now in this much larger Hilbert space a phenomenon which is called an irreducible degeneracy. Okay, so there's a few things that you have to be able to manipulate when you go this way. But again, Zlatko is an expert on this, and it's entirely possible with caution.
If there are any more questions, everyone thank Pastor Devoret.
Thank you.